Okay. So, again welcome to the lecture. So, in these two talks we are going to briefly giving you some motivation behind the surface integrals, and then we want to again state two theorems, mainly divergence theorems and the Green's theorem. Things are little more delicate, even to state that theorems is not easy, you need some notions, but our course does not now allow to get into all that details, because that is not our aim of this course. So, just you understand. So, we want to tell you the surface measure and surface integration, surface measure and integration to begin with. Then we will, these are the two topics we want to discuss, and then the divergence theorems. So, in this case, so you try to understand, because we will be trying so the kind of motivation basically. Motivation. So, when you study a PDE, you will be studying boundary value problems, PDE, boundary value problems, right. Boundary value problems. So, you will have a PDE here, and you will have a, it is a boundary. So, if this is omega, the boundary is normally denoted by d omega, maybe sometimes you can denote by gamma or sometimes by other gamma. So, you come across all the time, you know how to integrate. So, if you have a domain here, if you have a, so you it will come across integration over boundary, that is where the integration over the boundary, which is a lower dimensional subspace boundary. So, you will have a boundary d omega, maybe is a curve in R2, right, curve in R2, or it will be a surface in Rn when you go higher thing, surface in Rn. That is why need to introduce a measure. If you look at the Lebesgue measure, so let me quickly call what is Lebesgue measure, right. You need a measure to integrate. So, how do you compute your mu 1? So, this is the in Rn, or this is also denoted sometimes by dx, you can one dimension, sorry. So, let us start with R1, measure R. This is based on the concept of mu 1, if you take an interval I, it is the length of I. That is what you do it in one dimension, that is a flat domains, right. It is a concept of flat domain, and then using this Lebesgue measure is developed to measure the length of arbitrary sets. Of course, you can't do it for all sets. So, there are some notions like measurability and all that. End of it, you will be able to define what is an integration. So, you can talk about integral of fx dx over measurable sets. Let me not get into all that measurable sets and all that concepts, but then you can do it mu 2. It's a, so this is a based on the area concept, right. So, this is basically gives you mu 1, the one dimensional Lebesgue measure basically gives you the length of the interval, and mu 2 gives the area of that, mu 3 gives the volume of that. In general, mu n gives to the volume, that is a very general notion of that one. So, that is a concept you want to do it. So, when you have a domain with a boundary here, so if I take a boundary, I want to measure it. So, let me little more define. So, if you have a curve, the curve can be here. I want to define a measure gamma d gamma here, and if I take any, say in the along that set, if I take an arc or a piece of that, say from P to Q, I want, if I integrate PQ, these are all I want it basically. I want the length of PQ. So, you see, I cannot use one dimension, it looks like one dimension, it is one dimension in some sense, but then I cannot use because this is not flat domain which you are doing it. It is not R, R1, R2 etc. It is a curve sitting in R2, or it can be a curve sitting in any Rn, R3, R2, R4, you can see that curve. So, but end of it, the length of the curve you want to. So, you want to, and more generally, if there is a function defined here, function f defined on gamma, it is not in R, defined on gamma, I want to define what is f d gamma. This in one dimension, you already know that these are all line integral, but then the idea behind that is some sort of a measure which I am going to tell you soon. And more generally, if you have a surface, I want to define a surface measure, and then if I take any region here and if I integrate over that region with respect to ds, I should get my area or volume of the volume or area, depending on, there are different notions of that, and this is what I want to actually do. So, I need to have a measure, I should be able to measure. So, they get the idea of the Lebesgue measure, but then it is what we call it a, in some sense, idea of flattening. But then the issues will be enormous. Okay. So, let me start with a simple case, then we will first we understand the simple case which you are already familiar. Okay. Suppose the curve is given by a function, curve gamma is a graph. So, let me do that. Okay. Gamma is a graph means I have a function here. So, let me use this one. So, I have a function here. That means the points on the curve gamma is of the form. So, your curve gamma is of the form set of all x f of x. So, this is a map f. You have set of all points of the form x f of x such that x is in an interval. A curve means a general thing. As you see, a curve in the previous picture, if you look at it, the curve can be any form. This is not given by a graph, but then what you have studied in implicit function theorem tells you that locally you can make everything as a graph. Okay, that is essentially the application of your inverse and implicit function theorem. You can locally you can get a graph, you can write it in this form even in the general case. So, let us try to study. So, every point on this curve gamma, so I want to measure the length. This is easy. Okay. So, I take a point here, I take a point close by point, suppose x plus x delta x. I do this one. So, let me put the curve. So, if I have delta x here, this looks like a, okay. So, I have a x here, I have a delta x here. So, I have a secant which I can do that. So, this is delta x, this is delta y. So, you have a delta x here, delta y here. So, your delta gamma square is approximately, if you look at it, delta x square. So, I am only giving in a very intuitive picture. you have to make it very rigorous, which and there are much more general theory if you want to learn it. So, your delta gamma is approximately square root of, I write it in a specific form, delta y by delta x square into delta x. So, this in the limiting case. So, now you do a limiting analysis, then you can see that this implies. So, delta gamma is approximately this number, and then make that your partitions and then do the limiting you. So, this is precisely a small element of the, it is actually a small element. So, this is a small element delta gamma, you see, and that, and hence the length of the curve gamma will become integral a to b square. If you put it, you get it y is equal to f of x. Okay. And then square root of this formula is familiar to you already. So, this dx corresponds to the Lebesgue part, Lebesgue measure, right. So, you are basically integrating here. So, this length is different from this length, but then just this length and you need this factor. So, this is the Lebesgue measure and your d gamma is basically given by this measure, you see. So, this is the square root of 1 plus f prime of x square, dx is the one you have to multiply with that one. So, you have a multiplying factor together with your Lebesgue measure, looking at this here. So, that is the kind of intuitive picture you want to do. So, this what we call it a line measure, right. You can call that is a line measure, and then this is a very one way of representing curve. So, there is a parametric representation. So, let me write that also. I will recall this later, parametric representation. Okay. So, this somewhat give immediately an idea if you want to find a kind of measure, and I will anyway come to back to this one more about the its more about it soon. Okay. So, let me do that in a parametric. So, what is a curve gamma? So, you can write a curve gamma in a curve gamma. You have precise definition, get it into the literature. As I said, I want to motivate you. So, curve gamma can be written as in Rn, curve gamma in Rn. You use it 2 or 3. You can write it as a gamma 1t, etc., gamma nt, right. So, the curve gamma is a smooth map or continuous map from AB to Rn. You assume it is C1 also for your understanding. Okay. All right. Some people this also represented by sometimes x1t, etc., xnt. You can do that one. So, if you do the same procedure, which I do not want to repeat more about it. So, you can calculate the length of the curve gamma in the parametric representation is nothing but integral a to b square root of, this is the same in the previous case, but then gamma I of t square 1 to n dt, you see. So, you have your length of the curve gamma. Okay, so, you have your, so in this case the advantage is that you can use any, so the curve will go from somewhere. So, the curve is a mapping which you have to understand. So, you have your AB here, you have your AB and you have your Rn here. See, this is your Rn, this is whole your Rn, and the curve can be anything. So, A may go to here and will go here. okay, and that is what you are calculating the length of the curve. So, this gives you what we call it an arc length variable, right. You can define arc length variable. So, you take a point here, take any point and calculate the length from this is corresponding to A, this is corresponding to, this will be corresponding to gamma A, and take any point corresponding to gamma t at some point t here. This is B, this will be your t. So, you can define what is an arc length variable as, that will be a function of t, this is nothing but you integrate a to t, and this is a one variable integration, you see same thing. So, here in the previous case gamma I, yeah sorry I did not write here, is a gamma I prime t, okay, gamma I prime t square dt. So, this is the arc length variable. So, ds is your measure, ds is the line measure basically. These are representation, these are all symbolic representations. So, you can write your symbolically ds square is equal to summation gamma I prime t square dt, okay. You have to write that. This is also sometimes written as summation d xi square or dt I square, whatever it is, whichever depending on variable you are using it. So, you can have this arc length variable doing that. So, having studied that, once you have that kind of arc length measure, now suppose you can have the integration immediately. Suppose f is a function f defined on gamma, defined let me not use f because already there, h is a function defined on gamma. Then you have your definition, you can integrate h with respect to this measure ds. So, this is my definition, this is same as integral of a, this is over gamma integration. So, integral of h over ds arc length variable from a to b h of gamma t summation gamma I prime of t square root dt. As I said, this is your ds if you want, you can write that one. Okay. So, this is the way. So, this is the extra square root of summation modulo of gamma I prime square is what you are done, but this is a one variable integration, mu 1 integration basically. Okay. If it is smooth, it is the same as the Riemann integration, whatever it is. You know that this kind of thing HDS comes in higher dimensions as the work done and all kinds of things. So, you will come across such kind of things. Okay. So, there is also another way of, so this is also called the line integral. Okay, this is called line integral, and sometimes it is written as, sometimes it is written as integral. So, you have to be careful with this notation pxy dx plus qxy. I want to write this because this is where I will write my theorem. This is over gamma. So, be careful, the first one is not integrating with respect to x or integrating with respect to y. By definition, this is integral of a to b, where p and q are functions defined on that curve or in a domain surrounded by that one. Integral of a b p of gamma 1 of t, gamma 2 of t into gamma 1 prime of t. Now, it is a function defined on a b plus q of gamma 1 of t, gamma 2 of t, the gamma 2 prime of t dt. See. So, this is the definition you have to write it. So, the line integral is used this way, and you have to have this perfect correct definition. Keep that the right hand side is an integral of one dimensional integration, the standard one dimensional integration, and that is the way you have to interpret. And okay. So, with that let me go to some surface integral, about more about surfaces in R3. Or more generally you can have a hypersurface in Rn. Hypersurface means for example, in R3 you have the lines and the normal 2 dimensional surfaces. Of course, this 2 dimension, if you are not studied what is the meaning of dimension, which you probably have to understand by some other means. So, a dimension less, 1 dimension less, that is a hypersurface, because when you go to Rn and you view it Rn as a manifold, and then you know that you can have k dimensional manifold sitting there, and the n minus 1 that any surface having a dimension n minus 1 as a manifold is called the hypersurface. So, you can have your precise definition on this one. So, before going to that, surfaces can understand in 3 different ways. Okay. All will be useful at some. Okay. You can understand surfaces in 3 different ways. So, one as a graph. So, want to understand the function exactly whether as a graph. That means your surfaces S. So, suppose you call it a surface S can be considered as a points of the form x prime some f of x prime. I will tell you exactly where x prime is in V. What is V? V is a subset of R n minus 1 open. So, it is an open set in R n minus 1, and F is a mapping from V to R. So, basically you are having say 3 dimension. When I plot it here, you have a x1, x, y and that. So, you will have a domain V in R2. From that domain R2 you will have some map, and then you get your surface. You can, so, basically looking at as a graph globally. Okay. The one of the difficulty is that you may not have such a global representation, as I said. The surfaces can go in a more flat way. Okay. So, the another second one is considering it in an implicit form. So, you can consider surfaces in an implicit form. Okay. And then the implicit function theorem will tell you, implicit function theorem will give locally, you can write it as a graph, locally can write it as a graph. Okay. That is the one thing. The third one, so as I said, this is globally writing. The first one is a global writing, and then the second one is in an implicit form. When it is an implicit form, depending on the derivative, one of the derivative you will be able to solve in terms of the other variables. So, you can write the in a one way locally, and this of course creates trouble. When you introduce a surface measure, you will be able to introduce a surface measure locally, but then you have to develop that in a global way. For that you may require partition of unity and other kinds of things. As I said, these are little more delicate, but please go through it. So, the third one is a parametric form. That means you have a surface, it is given by your xi is equal to, you will have a family of functions xi is equal to fi of sum s prime. That means you again have a where s prime varies over Rn minus 1. Okay. Exactly, when you have a represented a curve in R2, you have gamma 1 t and gamma 2 t, where t is in AB. Here s prime is in Rn minus 1, varies, you get points. So, x prime you view it as an s prime, varies in Rn, some set in Rn minus 1, not varies in Rn minus 1. So, that is the varies mean varies in a domain in Rn minus 1. All right. So, let us now try to motivate the surface measure in R3, surface measure. So, let me first little bit motivation, surface measure and integral in R3. Okay. The motivation is fine. So, you have R3 here and you have a surface there, assume it is a globally defined surface. So, let us say it is a globally defined surface graph as a graph. So, you view it as a graph, surface as a graph. Okay. I said you can do it locally. So, what is the meaning of that? You have a you have a region here V, this subset of R2. Okay. This is your R3 totally. So, you have R2 R here. So, you fix a point here U naught V naught. Okay. And okay, when you fix a point here, so this is your function f. So, f is a f maps from V to R2. So, your surface S is given by, let me write it in a simple, this is the easiest way you can understand, set of all points x, y, z such that x is equal to, or graph or a parametric form, maybe parametric, that is also fine, that is some little more general. So, x is equal to f of u v, y is equal to g f g h. So, you have 3 maps g u v and z is equal to h u v. So, this is your surface. So, your set of all points. So, this u v maps to this surface here. Okay. So, let us try to understand this picture in a one more nice way. So, maybe go to the next page. Okay. With that we will do more later. Okay. So, you have a region here. So, let me note a thing. So, you have a look a small region. So, you have a surface here. What is our whole understanding? You have a surface here I want to understand a small region here, how to measure a small region on the surface. So, you look at a small point here. So, this is your u naught, v naught, and then when you look at the map, u v naught going. So, I am varying u. When I vary u, so corresponding to u naught, I will have an x naught, y naught, z naught. I will have a x naught, y naught, z naught. So, when I vary u along this line, it will move along a curve. So, you see. Similarly, if I move along this line, if I move along this line, I will have another curve. Okay. So, you will not under FGH will produce a curve on S, you see, curve on S. Similarly, if I fix u naught and vary v, I will produce under same thing a curve on S. So, what do I want to understand? So, if you have a small region here, so if I have a small region here, it will move corresponding to that a small region here, you get. So, this is the exactly this region is the surface area element. I want to know approximately surface area element. If I call this one is delta u delta v, and this is my, if the surface is S, that is my delta S. So, I want to approximately understand, I want to have an approximation delta S approximately. If I know that one, exactly what you have calculated d gamma, square root of 1 plus f prime of x square you have to do. So, for that I have to, what we have done in one dimension, I have to understand f prime of x. So, I want to understand this is my tangent here. Similarly, I have to understand my tangent here as well. So, these two tangents I have. So, when I move this one, the corresponding tangents will be f u, okay, at u naught v naught. I will get my g u and then I will have h u. That is a one tangent, and the other tangent is f v, same point, g v and h. I have my h v. So, I have two tangents, but there will be complications. Surface is defined as a map very generally. The whole area can go to some point. So, the surface in general can go to a point, the entire surface can reduce to a cramp to a single point, or it can go to a line. It is all possible under that mapping. I can define the entire mapping from a region to a point. I will be able to define a mapping to a curve. Otherwise, I may be able to define a curve like that. But these are not genuine surfaces. So, what is the meaning of genuine surface? Genuine surface is the one which we look for these two tangential directions. So, basically these two tangential directions which you give here will define a tangent plane. I have to get a tangent plane there, that is equivalent to saying that the linear independence of these two. That is what you have to understand. So, you have the linear independence of these two vectors will tell you the genuineness of the surface. Otherwise, there will be degenerate cases. I can define a map from an R2 region in R3, everything going to a point or a line or a combination, all kinds of things can have, degeneracies can happen. That happens, so there may not be a surface, all these can vanish. Okay. So, you can have these two vectors can vanish if there is a constant function. So, everything can happen. So, you have to avoid all that and you have to see that these two vectors obtained are linearly independent, which is equivalent to saying that linearly independent equivalent to saying that you have your Fu, Gu, Hu, Fv, Gv, Hv has rank 2, has rank 2. Okay. So, I will continue this little more, I do not know how much time I need to finish. So, we conclude for this stage. So, you get to know this kind of idea about the surfaces and the tangent plane and the normal plane which we are all required. Okay. So, we will continue the lecture in the next. Okay. Thank you.